In this video, we're going to take a look at how to do transient analysis with our op-amp circuits. And so this type of transient analysis we can use in other circuits as well. So as part of your pre-lab, you're actually going to have to do this type of transient analysis. So I wanted to make sure everybody's familiar with how to do that. So what we're going to do, I have our op-amp circuit from the previous video here. And of course, we were doing a bias point simulation. So we had this DC voltage source. So if we're doing a transient analysis, we're looking at an AC voltage source. So we're going to want to get rid of this, and we're going to want to replace that with an AC source. In particular, we're going to want to replace it with a sinusoidal source. So we also have VAC, but our VAC is going to be more for steady state AC analysis. So if you're wanting to look at plots over time, you're going to want to go with this sinusoidal source. So I'm going to double click that. I'm going to place it right in here where our DC source was. And hit escape to stop placing that. And so let me sort of move this wire over a little bit so we have more space to see all these variables here. So notice I have several things here to fill out. So let me just double click on this. And so actually let's stay on this page and let's just do one at a time. So we have a V off, which is our offset voltage. And so that's just how much this sine wave is above or below our x-axis. So in this case, let's just keep that at 0. So we're saying it's centered on the x-axis. Our amplitude, so in this case, let's keep it relatively small so we can easily see everything. Let's make it a value of 1 volt. So okay. And then frequency. So for our frequency, let's say we want to do 1 kHz. So again, notice I'm not having to put units, but it is important to include these prefixes, K for kilo, M, capital M for mega, stuff like that as you're doing these circuits. And then this AC part, we can just leave blank for the basic transient analysis. So the next thing we're going to want to do is set up a new simulation profile, because right now we only have this bias point simulation profile. So what we're going to do is do a new simulation profile, and let's say we can call this our transient analysis. And so remember, we cannot have any spaces when we name these simulation profiles. It'll get upset with you and it won't open them. Okay, so now we're staying in this time domain transient analysis type. And so again, we're not going to have to adjust too much over here, but we can make some adjustments. So our runtime is basically how much time this is going to simulate this for. So what it defaults to here is it's going to simulate this for 1000 nanoseconds. And so you might have to adjust this depending on your frequency. So in this case, remember we put a 1K frequency. So that means our period is going to be 1 millisecond. So let's say we want to see 2 periods. So we could come in here and we could say run to 2 milliseconds. And so you can have the S or you cannot have the S, either way should be fine. And so we'll come back and we'll talk about this maximum step size here in a little bit. We're not going to be concerned with this start saving data after, but where that would come into play is if maybe you had an element like a capacitor or an inductor that's charging up, and maybe you want to neglect that initial charging up phase, so you could say just start saving data to be plotted after a certain time. Okay, so we've adjusted our time and that's it, so let's just go ahead and click OK and see what we get. Okay, so we've selected our transient profile. So notice we can switch back and forth between our profiles now, but we want to be doing transient. So let's go ahead and click play. And our PSpice is working on it. And it's going to open this new window again with our simulation results. So it's working on it, and so now we're at 100%. And so notice, unlike with our bias simulations, now we have this black background and our x-axis plot with time as our default. And so that's because now we finally have some information that we can plot. And so we could still go here to view simulation results, but it's going to be more interesting to be able to plot stuff. Okay, so in order to add a plot, what we can do is we can click this Add Trace button. And so this is going to bring up a new window, and from this window we can select any of these variables here. So notice there's sort of a lot to sort of parse through. We can make this a little easier. In this case, let's say we want to look at our input and our output voltage. So we can deselect powers and currents because we're not wanting to look at those. So that can be a helpful way to sort of look at certain things. We'll notice that for each of our sort of voltages, we have several options. We have, for instance, VR1, VR1 colon 1, VR1 colon 2, and so that's just one side or two side. Typically, we're just going to be sticking to using these node voltages. So notice last time we had used a net alias to label our output as output node. So I can click output, and that's going to plot our output voltage. So let's click OK. And here we see a plot of our output voltage. So we notice it's centered on the 0 volts, and we have a period of 1 millisecond as predicted, and we're going up to 6 volts. So our gain of the amplifier hasn't changed, so we left our resistor values at 5K and 1K. So for this non-inverting amp, our amplification or gain is 6, so our input had an amplitude of 1, so our output is going to have an amplitude of 6. So let's go ahead and plot our input as well. So we can note that this node for our input is 00194. We could have also placed a net alias. So let's go to add trace, and we still just have only voltages selected, and I can look for VN00194 and select that. So we're not going to need it in this lab, but notice as well over here on the right, there's also a lot of options for operations and sort of different things that you can do with various curves. You can find averages, you can do the decibel value, you can do imaginary, a lot of different calculation values that you can do here. So that will be helpful to you in later classes. But in this case, we're just going to plot this voltage. And so here we see it in red. And so we notice that this one, so it's in phase, so we have sort of the peaks aligning, positive peaks aligning, and negative peaks aligning. It also has a period of 1 millisecond, and we can see here that the amplitude is only 1 volt as opposed to the 6 volts for our output. Down here, we also know that we see that we have the labels for the various curves. There's a lot of other functionality that we can do. I'm not going to cover all of that right now, but for instance, one simple thing, if we want to play around with this trace, we can do trace information to see where it comes from, or we can do trace property, and we can adjust the color, the pattern, the width, the symbol, things of that nature. So there's a lot of other stuff we can do, for instance, with cursors, finding maxes and mins. A lot of this is listed in the PSpice basics document, and if you look on the page titled Plotting Tips and Tricks, that has a lot of useful stuff there. One thing that's particularly useful if you're putting these plots in other documents, you might not want to screen capture and have this black background, particularly if you're printing. So what you can do is you can click Window, copy to clipboard, and then once you paste that to somewhere else like Microsoft Word, you should have a white background, and that's going to be easier, particularly again if you're printing. So now we're going to take a closer look at that option in our simulation profile about maximum step size. So let's say for some reason for this 1 kilohertz wave, instead of wanting to look at 2 periods, we want to look at several periods. So I'm going to come in here to edit our simulation profile, and let's say instead of 2 milliseconds, which was 2 periods, now we want to look at 20 milliseconds, so 20 periods. So let's just leave this maximum step size blank for now, click OK, and run our simulation. Okay, so PSpice is working on it. So again, it's going to pop up a new window. If you've not closed your window from last time, it'll just populate in that same window, and you'll have to click on that to see the results, of course. Okay, so 100% complete. So let's go ahead and maximize this. Let's add our traces. So we have, let's look at just our voltages. We want our input voltage and our output voltage. So both are going to be plotted. And we get something that looks like this. So just from sort of this high level view, we can see we have a lot of these sort of peaks. But if we want, we can come up here and we can zoom in, zoom out, zoom fit, or zoom area. So let's zoom area. And let's see if we can take a closer look at approximately 2 wave periods like we saw before. And so, of course, this looks a lot messier than what we saw before. We see these sort of jagged lines. And so the reason for this is as PSpice is doing the simulation, it's basically stepping through data points on this sine wave. And so if those points get too far apart, we end up having this sort of jagged, rougher approximation that we're seeing here. So let's see how we can fix that. So if we want to fix that, let's go back to editing our simulation profile. And what we want to do is we want to change this maximum step size. So let's say, for instance, we have a 1 millisecond period. So let's try doing 0.1 milliseconds, so a tenth of the period. And so let's see if that makes any difference. And so a lot of times this is just kind of playing around, getting a feel for it. So let's run PSpice again and check out our plots. Okay, so it's working on it, 100% complete. All right, so let's plot these. Input, output, okay. And so we notice it's still pretty jagged. So again, we can zoom in on one area. Oops, let's have to hold this down. So let's hold. Okay, so let's try this one more time. There we go. So there's our zoom area. And so we see it's still pretty jagged. So let's try to decrease that even further. Let's come back here, edit our simulation profile. And so the trade-offs here between making this smaller and keeping it large is the smaller we get it. So for instance, now let's try 10 nano. The smaller we get it, the longer it's going to take to run the simulation, but the better the waveforms are going to look. So let's go ahead and play that. So we might notice this taking some time now. So notice now this isn't instantly going to 100%. So it's actually taking a little bit of time to process. And if we had done even a smaller maximum step size, that would be taking even more time. So it's still going at a pretty fast pace here. And we can see the time that it's at in the simulation here. So right now it's at 15 microseconds and we were going to 20. And it's just about at 20 microseconds. And there we go. And so when you have a lot of data in the file, you'll get this message here. And so basically it's saying there's too much data to sort of keep track of all at once. So you can either look at a small part of the trace with everything or the whole trace with fewer points. So let's go ahead and look at fewer points for now. And so that's a good sign. So that means hopefully our curve is going to be a little smoother now. So let's look at our input and our output. Okay, so just from sort of high level here, it looks a lot better. So let's do our zoom area. And again, let's sort of try to look at roughly 2 periods here. And so as we can see, this is a lot smoother than what we did before adjusting that maximum step size. So that's one way to sort of clean up your plots. Of course, another way, we notice here that this is a lot more data than probably we need. So maybe a better thing to do instead of playing around with your maximum step size is to take a step back and say, well, I really only need maybe 3 or 4 periods. So you can decrease that runtime in the simulation profile as well.